Okay. Hello, everyone. Today we're going to cover the fourth DP problem from the prelim review slides. So this is going to be a good review about how to actually determine what's your recurrence correctly and develop the backtracing algorithm. So let's head straight into it. Here's the setting. You're given two machines, machine A and machine B, and at any time step, if a machine is turned on, it will produce some positive value, namely like A1, A2, A3, all the way to AN, B1 for machine B. And the goal is to figure out a schedule for when you should turn on A and B in order to maximize the total sum of the values produced. Now we have some constraints. Constraint one is that only one of A and B can be turned on at the same time at any time step. And furthermore, if you want to turn one machine off and then the other, it will cost 1 unit of time. So switching between A and B will require 1 unit of wait time. So for example, on this example above I have here, you could imagine a schedule which sticks with just A. If it sticks with just A, then the value accumulated, if A is turned on for all 4 time steps, I just noticed a little typo, then the value will be, well, accumulated 28. If instead we had a schedule that just sticks with machine B being turned on the whole time, then we would accumulate the value of 26. And I can also show an example of a schedule which switches machines. So we could start with B, and then we could switch to machine A. So it would skip time step 3. And in total, it would accumulate value 31. And this turns out to be optimal for the example. Anyhow, now let's try to figure out how this DP works. So the main thing is first figuring out what your dynamic program subproblem is. And a lot of that is also figuring out what's your inputs. So let's go over a simple approach. What seems like a useful input? In this problem, time is very important. And you can imagine finding the optimal solution for a smaller schedule. So that's exactly what we'll do. Let's say we have an op table that takes in a time I, and we'll compute what's the maximum possible value you can get from the first I time steps. Okay, so if we try to solve this, what ends up happening is, and I'm going to include time step 0 here because it's nice for to consider the schedule before when without any time steps. So at I equals 0, no machine is run, so we get 0 value. Of course, I'm looking at this example that we have here. At time step 1, let's see. At time step 1, we're gonna want to run A. So we want a value of 2. Okay. At I equals 2, we can actually, at time step 2, we can actually start looking at some recurrences. So time step 2, if I consider running A at time step 2, I could use the previous subproblem at time step 1, which I know has a value of 2. Unfortunately, that's not the optimal solution here, though. The optimal solution actually will involve B, running B for both 1 and 2. Unfortunately, nothing in our table tells us anything about any subproblems we can use to compute that. We'll just have to recompute the whole path, the whole schedule just using B. So this is kind of where this approach fails. The recurrence, even generating the recurrence is really hard to do, and we'll have to recompute a lot of values. So we should try something else. Importantly, there's this really important thing to know, like which machine are we running, right? That would be really cool to know. So another approach we could take is actually storing the machine and the optimal value as a tuple for each time step I. So it's a slight modification to the previous approach, very similar though. But we'll see that it also, although it fixes the recurrence, it fails because backtracing will be very, very difficult. So we can also say the optimal value for I equals 0 is 0. Here, time step 2, it would be optimal to use A, 1. But at time step 2, it would be optimal to use B. And we can see that these two subproblems, they have no relation to each other because one uses A at time step 1, the other, this B here, it must use both, B must be used at both time steps. So if we actually try to do backtracing starting at t equals 2, then we wouldn't be able to use any information from I equals 1 about where to go. In other words, we'd be blind to try to backtrace through this DP table. There's not enough information to go off of. Which brings us to our third approach. Often, what's better than just incorporating a tuple into the opt table is to actually increase the dimension of the opt table. We've mentioned that it's important to know which machine A or B is running. So let's actually incorporate that. Let's not only take in time as a factor, but which machine. And as a note, because there's only 2 machines, it's easier to just write these out as 2 one-dimensional DP tables. So let's do precisely that. Let's have one DP table for knowing when to run machine A at time step I, and let's have one for knowing when to run machine B at time step I. Okay. So this is, so for this, we try to run A at time step I, and we want to get the maximum, we want to store the maximum value we can get for a schedule from 1 to I. Furthermore, it'll be the same thing for B, but we just want to run B at time I and return the maximum value for a schedule for the first I time steps. Okay, let's see how this plays out. So in this example, we have I equals 0, 1, 2, 3, 4, as well as opt of A and opt of B. And now at time 0, nothing has happened so far. So we'll just say these values 0. At time step 1, well, we know for opt A, we're going to have to run A. So that's going to have a value of 2. For B, well, we know we have to run B first. So that's going to have a value of 1. All right. How about time step 2? The time step 2 for opt A, we're going to have to run A, getting a value of 1. And then, well, let's see, where else could we have gone? Well, we could have gotten here from A at time step 1. And in fact, that's given to us as a subproblem. Here, this subproblem with 2 here. Since we gained value 1 at T2, the new optimal value for opt A is 3. For opt B, now we start at 10. And we can only come from here from B also at 1, right? Which is this subproblem. So 10 plus 1 is 11. Okay, and then we can do something similar for 3. 3, we just have to consider one more case. So for example, from something like 5, there's 2 ways we could go about this. Either we just came from A, or we just came from B. But B has to be one more time step back because the rule is when you switch between A and B, you have to wait a time step. In this case, that corresponds to the subproblem opt A of 2 and opt B of 1. And so which one would you rather add the value of 5 to? You would want to add the higher one, 3. So 3 plus 5 is 8. Okay. And then you do the same thing for this bottom one. So B is 5. We're considering the subproblem here and here. So we'd want to add to 11. So 11 plus 5 is 16. And then similarly for 4, you can do this if you want. 31, and we'd get 26. Okay. So the nice thing about this opt table is that it was really easy to compute. And generally, if your opt tables are easy to compute, that's a good sign. And it's going to lead to easy proofs. We're not going to go over proof of correctness here, but you can see some in the slides. Okay. So it seems okay. Let's try backtracing because that's really important. That's our previous approach failed because of backtracing. So what is the optimal value that I'm building off of? Like, what's the actual optimal? Hold up. I have low battery. 1 second. 1 second, folks. Hold up. Oh yeah. All right. We're gonna be at an awkward angle here, but bear with me. Okay. Um, okay, backtracing. So what is the optimal value that I actually like need to compute here? I need to compute it's this 31 here, right? This 31 is telling me that the optimal schedule across all 4 time steps gets me a maximum value of 31. And particularly what this tells me is that the machine I use is A at time step 4 because it's on the top row, right? Opt A. Okay, now how can I figure out how to move backward? In this case, what subproblems does opt A of 4 rely on? Opt A of 4 relies on either it just came from A at time step 3, or it came from B at time step 2. Well, we know that A at time step 4 has a value of 20, so the value we get is not changing. The only thing that changes is how much value do we get from a previous subproblem. And in this case, the subproblem with 11, opt B of 2 has greater value. So that's exactly what we're going to put in our solution. We're going to use B and transition over to A for time step 4. All right. Now, how do we get from B? How do we build more of the schedule? So B, what does B rely on? B relies on, well, it can really only come from one place. From being B again. But another way you could look at it is, there's this zero here, and maybe the initial state of the machines is that A is on at time step 0, not producing any value. In any event, because only positive values are produced, we are always going to stick with this B here. So this tells us, as expected, that we run B at time step 1, and so we have our schedule. So backtracing is surprisingly easy. The only thing left is to formalize this in terms of actual formulas and the backtracing algorithm. So let's do it. Okay. So we'll start with the base cases. Yeah. Okay. So base cases, let's see, at time 0, none of the machines have produced any values, so we should expect no value. So opt A of 0 and opt B of 0, it makes sense that we set them to 0. We are also going to include t equals 1 as a base case because it really doesn't rely on anything. T equals 1, the machine that is ran at t equals at time step 1 is already specified by which opt we're in, opt A or opt B. So, opt A is going to produce the first value that A produces, A1. And opt B is going to produce the first value that B produces, which is B1. So it's just the first value produced. Okay. Now everything else is going to rely on subproblems. So now we can head into our recurrence. Okay. So let's think carefully about this. We're going to be at some time step I greater than or equal to 2 because everything else was covered by our base case. I guess you could say, bounded by n. And we're also given that we start at some either A or B. All right, so let's just say for fun, we start at A at time step I. Now, what are the two subproblems that we can use to get to A being on at subproblem I? Well, either, case 1, either A is already on at time I minus 1, or, just making sure I'm recording this, or B is on at time step I minus 2, and you switch to A, waiting for one time step. These are the only two subproblems as given by the problem. There's only 2 machines. And so now we have our recurrence. So for opt A of I, and don't forget, at A at time step I produces some value AI. So we're going to want to add some value AI, and we want to maximize it over these 2 possibilities. So let's take the max. Possibility 1, A is at time step I minus 1. Well, that's just, we actually computed that. That's opt A of I minus 1. And how about B at time step I minus 2? Well, we also computed that too. Let's just opt B of I minus 2. And there we have it. It's pretty similar for B. In fact, it's completely symmetric with respect to A and B, where instead you just add the value of B and you switch A for B, basically. Same reasoning. Okay, so we can see these are pretty simple base cases as well as recurrences. And now we can move on to backtracing. So we're going to skip over the proof of correctness because it's pretty standard induction on the recurrence, and you got a lot of practice in that for the homework. Anyways, let's try backtracing. So what's the actual algorithm we're going to need for backtracing? If we look at what we were doing before, we started by looking at the last column. We took the max value. Why did we take the max value? Because we want a schedule that produces the highest value. So we take the one with the max value. And then how do we know which subproblem to go back on? Because remember, backtracing, what backtracing all about is it's about tracing the solution through the recurrence and base cases, I suppose. So how do we figure this out? Well, we looked at either we continue using A or we switched from B, and we said, oh, which one of these is higher value? Why? Because simply the subproblem that has higher value is the one that's actually going to be used for the optimal solution because we want to maximize value. So what we had to keep track of is, so you notice that either we go back one time step or two time steps, which can be very confusing. So we'll have to keep track of the time steps as we trace back through our solution. So we'll have to keep track of time. And we should also keep track of which machine that we're using, right? Because the difference between A and B is incredibly important. And we want to be tracing back to find out which machine is activated at which time. So let's form this algorithm. Let's say S is the set of, let's say, tuples, which consist of machines and times which you want that machine to turn on. We'll see more of that later. So this is the schedule. Now, I said we want to keep track of time. So let's do that. And I said that we also want to keep track of the machine, right? So the first machine we need to take care of is the one all the way at the end for N. So let's say M is that machine. And we're going to find out exactly which machine has the bigger value. So we'll take the argmax of the optimum value at the nth time step. Furthermore, we'll also initialize an index starting at n so that we can, backtrace later on. Okay, so now we want to keep backtracing until our index hits 0. So while I is not equal to 0, what do I want to do? I want to start building my schedule. So what do I know at this point? At this point, I know what machine I'm using. I'm using the machine that optimizes the solution, and I know what index I'm at. So I already know I'm using machine M at time step N. So I can just say append MI to S, right? So this is telling me, when I should use M and at time step I, which is N here. Now I need to figure out how to go back through my recurrence. So recall that I consider these two subproblems. Now to actually compare the two cases, I'll need to find out which of the two have a larger optimum value. So either A, I really shouldn't use the letter A here. Either I stick to the same machine M but I go back one time step, or I go to the other machine. I'll call this M bar for the other machine. And I'll go back two time steps because I need to wait one time step to actually transition. So in this event, if the left value is greater than the right value, that means that the better subproblem is to stick to the same machine. So I'll make sure to recurse by the machine will be the same, but the index will decrement by 1 because I went back one time step. And then if I just end it there, from this point on, it'll go back through the while loop as long as I haven't reached 0 yet, and it'll add that next pair. It'll add that subproblem we saw, this one. Anyways, that's not optimal in the example. Now there's that other case, the else case. Else this right value is greater than or equal to the left value. So in this case, that means it's at least better to switch to M bar, switch from M bar two time steps ago, which means that the machine we should be considering is M bar, and we should move back two time steps. Okay. So those are the two recursive cases. I will do a while loop until we reach the end. And then finally, at the very end, we'll return S, which is the list of tuples, which the left side tells you what machine, the right side tells you what time step to run that machine. So we can see the backtracing is actually a very simple algorithm. The recurrence is simple. All of this kind of came forth from introducing this new dimension into our opt table. And we got that intuition by working through simpler cases and seeing where they failed. They failed at the recurrence, they failed at the backtracing. Okay, so that's this dynamic programming problem. Like as a general overview, we looked at the problem, we developed the subproblem, as well as what's the actual input space of the opt table. We further formalized it by developing the base cases, as well as the recurrence relation. And finally, using this example, which was very helpful to figure out what I'm actually doing, I was able to work through the backtracking algorithm. Okay, so thank you for watching. Post any questions. Please leave any questions you have in the ed post.